Let's start about the QR decomposition using householder transformations. Mr. Householder was a man, I don't know, living 200 years ago, and he pondered about how can I do an orthogonal transformation to get zeros in the first column. And maybe we can start with that picture. This picture here is the idea of Mr. Householder. This vector here is the first column, and I want to get zeros in the first column. And the idea is that if we take that vector, we have to invert here. If the arrow is on that side, it should be on that side. And we can take that arrow and split it into the sum of these two. And then we want to invert this one to that one, and we want to keep this one. Okay, this is the result of Mr. Householder. After thinking 1 week about the problem, maybe he got that, and he said using an omega is a vector, for example 1, 2, 3, and starting with that omega and then constructing a matrix with that structure, then I get what I want to. So, okay, this is a matrix. Let's make clear what are the elements. If omega is a column vector here, then omega transpose is a row vector times a column vector. Row vector times a column vector is a number. So here we have 2 divided by some number. And omega, if omega is a column vector times a row vector, the result is a matrix. So we have here a number times a matrix, which is a matrix, and this is identity matrix minus some matrix, and the result will be our H. Okay, we will see an example later, but now we want to analyze some properties, and one of the most important properties is this one. If we multiply this matrix H by omega, then we get minus omega. Why do we need that? We want that this vector becomes that vector. Okay. And this is really true. Why? This is our H matrix, and if we multiply this H matrix times the omega vector, then we have parentheses here and here with a matrix minus some other matrix. And the rules of matrix calculus tell us that we can multiply each element. So identity times omega we have here minus then this part times omega, and this we have here. Okay, then identity times omega is omega, and then here we have a product of 3 matrices or row and column vectors, but these are also matrices, and we can set the parentheses as ever we want. So far the parentheses were that way, but now let's rearrange the parentheses that way. So that's what we're doing here. And what do we have? Then omega transpose is a line times omega is a column, and line times column is a number. And which number? It's the same number as we have here, so they two cancel out. Mathematically that is really interesting, and it's true. Okay, so this cancels, and then we have omega minus 2 times omega, and this is what we have here, and something minus 2 times something is minus something, so we get minus omega. So in total, H times omega is minus omega. And now for vectors which are orthogonal to omega, let's revisit our picture. For this vector, this is orthogonal to the red vector here. This vector should be kept, and now let's analyze if that is true. Okay, if we have that, H times V, H is again identity minus 2 times and so on, times V, so E times V here and that one, and then minus 2 times that times V again. That's what we have here. let's rearrange the parentheses. Because V is an orthogonal vector to omega, then here omega transposed is a vector of that type, V is a vector of that type. If we multiply them, then we get a number. Because they are orthogonal, it's the number 0. And having a 0 here, that means 0 times that is 0, 0 times that is 0. So this is completely 0 vector in that case. And we have E times V, which is V, and so in total we get is V. So H has the desired properties. Now let's check if H is an orthogonal matrix. It is, yes, but why? Can we really understand that? Yes, we can. We can check. H is orthogonal if H times H transposed is identity matrix. That's the definition of orthogonal. So let's multiply. This is H. This is H transposed here. So let's first do this transposition. How can we transpose? If we have a sum of two matrices, transposing means transpose the first part, take the minus, transpose the second part. Okay, that's what we have here. Identity transposed. And then this is a number, so transposing it does not change anything. So this is kept. But now here, this is a matrix. So transposing a product of matrices means swap the two matrices and transpose them. So it's the rule A times B transposed is B transposed times A transposed. So let's take omega transposed to be the first one and transpose that. That's what we have here, and then take that omega to the second position and transpose it. That's what we have here. Okay, what is a matrix? If you transpose it and transpose it again, you get the matrix back again. So here we have omega, because omega transposed is omega. And here we have omega transposed, nothing changed. And the whole rest is only a copy apart from that. Okay, what do we see? We see H transposed, we worked only on that part, is the same as H. So transposition does not change anything. That means that H is a symmetric matrix, but what we are really interested is if H is orthogonal or not, and now we can do that job. So how to multiply? If you multiply, you have a matrix plus another matrix times a matrix plus one more matrix. You can factor out, as you know, from normal numbers. So it's A times D plus B times C plus B times D. Okay, so identity times identity is identity. Identity times that part is that part. Then this times identity is again this. So we have minus something, so we have minus 2 times something, and so out of the 2 times 2 is 4, so we get minus 4 divided by, and the rest a copy of that. And the last part of the game is this times that. Minus times minus is plus, so we get a plus. And this is a number, this is a number. So multiply numerator times numerator and denominator times denominator. 2 times 2 is a 4. And this times that is this times that. And now we have to deal with the matrix. So omega times omega transposed, omega times omega transposed is omega times omega transposed times omega transposed. Okay, so let's rearrange the parentheses now in that way. So it's omega transpose times omega. This is a number. This is also a number, and it's the same number, so they cancel out. What is left? 4, 4. This one is that one. And this and that is that. Now we see minus that plus that, and it's the completely same that. So these two cancel each other, and identity is what we have left. And that means H times A transposed is identity, and that means A transposed is the inverse of H, and that means H is orthogonal. So when I was a student, the first time I saw these calculations, I hated that. I said, okay, that's complicated. But when I worked on that and I tried to understand every detail, then it came the moment when I understood every detail, and then I said, okay, that's nice. That's really nice. That's mathematics. But we will analyze completely in general. And now we know H is orthogonal matrix and H has the properties as desired. So let's check again everything we did so far, and let's assume omega to be some vector. If I do the lecture with people in one room, then I tell them, please give me one vector. 1, 2, 3 is a possible answer, but also -2, 3, -5, or whatever you want. So feel free to change this example and redo the calculation. Okay, what do we want to do? This is the H, and now we want to check what is the result if omega is 1, 2, 3. What is the calculation? Then we have H is identity matrix minus 2 times omega transposed times omega times omega times omega transposed. So let's do the calculation. 2, this is this 2, and then 1 times 1 plus 2 times 2 plus 3 times 3. That is a result of that matrix multiplication. Row times column is a number, and in this case it's 1 plus 4 plus 9, which is 14. And then here we have matrix multiplication, column times line. This is 3 by 1 times 1 by 3, so result is 3 by 3, and the result is 1 times 1 is 1, 1 times 2 is 2, 1 times 3 is 3. And then the next line, 2 times 1, 2, 3 is 2, 4, 6, and then 3 times 1, 2, 3 is 3, 6, 9. Okay, what do we have now? It's 1 minus 1 times 2 over 14, which is 2 divided by 14. 1 is 14 divided by 14 minus 2 divided by 14, which is 12 divided by 14. Let's step to the next position. Here we have a 0 minus 2 divided by 14 times 2, which is 4 divided by 14. 0 minus 4 divided by 14 is minus 4 divided by 14. Then here 0 minus 2 divided by 14 times 3, it's 0 minus 6 divided by 14, so we get minus 6 divided by 14. Please feel free to redo all these calculations as well, and then you will find out, okay, these are the entries. Okay, then what is 12 divided by 14? It's the same as 6 divided by 7. And here we can do the same. Minus 4 divided by 14 is the same as minus 2 divided by 7. And so we come from here to here. Okay, so now we have found our H. What are the properties of H? First, it's a symmetric matrix. These entries are the same, these are the same, and these are the same. So it's indeed symmetric. The reason why it's symmetric, we saw from here, going to here, going to here, and doing so we saw this is with the transpose is the same as without the transposed, and so it's symmetric. What were the properties? we said that h times omega is minus omega. Okay, let's check. This is our H matrix. This was our vector we started with, 1, 2, 3, and now let's multiply. 6 over 7 times 1, 6 over 7, minus 4 over 7, minus 9 over 7, it's minus 7 over 7, which is minus 1. So next entry, minus 2 divided by 7, plus 6 divided by 7, it's 4 divided by 7, minus 18 divided by 7 is minus 14 divided by 7, which is minus 2. So compare 2 and minus 2. Okay. And now let's do the calculation for the last row. 1 times that is minus 3 divided by 7. 2 times that is minus 12 divided by 7. So in total minus 15 divided by 7. Minus 6 divided by 7, which is minus 3. So in total, h times omega is minus omega, as we analyzed here. Okay, let's do the check for orthogonal vectors to omega. First, give me a vector which is orthogonal to 1, 2, 3. There are a lot of answers which are all correct. If this was a lecture with students in a room and me also in that room, then I say, okay, please give me a vector orthogonal to that. What means orthogonal? That means, okay, dot product 0. So one possible answer is 2, 2, minus 2. Multiplying with 1, 2, 3, we get 2 plus 4, which is 6, minus 6, which is 0. So indeed, this is 2, 2, minus 2 is a vector orthogonal to 1, 2, 3. And what is the result? Okay, let's multiply. 2 times that is 12 divided by 7, minus 4, 8 divided by 7, minus 6, no, plus 6, so it's 14 divided by 7, which is 2. Then this entry, how do we get? Minus 4 divided by 7, plus 6, 2 divided by 7, plus 12, 14 divided by 7, which is 2. And now this entry, 2 times that, minus 6 divided by 7, minus 12 divided by 7, so minus 18 divided by 7, plus 4 divided by 7, so it's 14, minus 14 divided by 7, which is indeed minus 2. So in total, h times v, this v is v. So h has the properties we proved that it has. Okay, we see it again for numbers. So now we come to elimination process. We want to eliminate, and this is our last piece in our puzzle. We want to map that vector to the axis, and that means that all the entries, here in our case we have a two-dimensional image picture, and so we have 1, 0, but it also works for 3 or even 4, 5, 6, 7, 8 dimensions. Okay, so we need that omega. This is, what is that? This vector is minus that vector plus that vector. So plus that vector minus that vector. So it's a, this is that vector plus that vector, and then minus that vector. So minus a multiple of the vector 1, 0, 0, 0. And instead of minus, you can also choose plus. This is that picture. And how to choose, I tell you here. If the first element is positive, then use plus. And if the first element is negative, then use the negative one. We also will see that in an example. Here is our example. And now the complete example, okay? This is our matrix, and what do we want? We want to cancel these entries. We want them to become 0, 0 by an orthogonal transformation. how do we do that? We take the first column. This is our omega. No, it's not our omega. It's part of our omega. And then this entry is negative. So we use the negative. And then the length of that vector. So we need the length of that. The length is -1 squared, which is 1, 2 squared, 2 squared. Add them, it's 9. Take the square root, it's 3. So the length of that vector is 3. And this means that in our example, this here is a 3. And here we have the 3 and we have a minus because this entry is negative. Okay, and then minus 1, 0, 0. And now we have -1, 2, 2, minus 3, 0, 0. So we get -4. And here a copy of that, 2, 2. This is our omega. Now let's construct our h, which is identity minus 2, this transposed times that. What is that? -4, 2, 2 times -4, 2, 2. So it's 16 plus 4 plus 4, which is 24. So 2 divided by 24. And then our omega vector, so -4, 2, 2 times -4, 2, 2. And the result is 16 -8, -8. Then this line, -8, 4, 4. And then again -8, 4, 4. Okay, this is 1 divided by 12. So 1 minus 16 divided by 12. 12 divided by 12 minus 16 divided by 12 is -4 divided by 12. And then take the 4 out of, and so we get -1 divided by 3. Then here 0 minus 8 divided by 12 is -8 divided by 12. Then take the 4 out of the denominator and the numerator, and then you get 2 divided by 3, negative, negative, so a positive 2 divided by 3. And let's do the same for all the remaining elements, and you will get this matrix. This is our H, and now let's apply that H. So if this is our Q1, let's copy A here. And what do we get? So here is our A, -1, 0, 1, 2, 2, 1, 2, 5, -1. And now let's do the calculation. -1 times -1 over 3, so we get 1 divided by 3 plus 4 plus 4, so we have 9 divided by 3, and that's our 3. Okay, next entry here, it's this 0 times that is 0, 2 times 4 divided by 3, and then 5 times that is 10 divided by 3, so it's 14 divided by 3, and this is 4.66666. So next entry here, let's calculate that one. So 1 times that -1 divided by 3 plus 2 divided by 3 minus 2 divided by 3, so it's -1 divided by 3, and that's what we have here. And now the interesting entries are these, the zeros. Are they indeed 0 or not? So -2 divided by 3 plus 4 divided by 3, it's 2 divided by 3 minus 2 divided by 3. This is indeed a 0. And so you can do the calculation for the remaining 5 elements. Please feel very free to do that. When I was a student, I always did every calculation to see if I completely understood or not. And so we know Q1 times A is that, or if we multiply with Q1 transposed, which is the same as Q1 transposed or not, because it's symmetric. Okay, and so we can write it also that way. And now we focus only on that block, and that means here we take this 1, 0, 0, 0, 0, and so we can forget for the moment everything and only focus on that block. So this is our new part of omega, and we redo the calculation. So this is what we have here, minus 1, 0, and then the length of that. Take your electronic calculator and you will find out this is the length. Square that entry, add them and take the square root, and you will get that number. And because we have here 0, we use that minus again. If that was a plus, then we would have used a plus, but it's a minus. And then we get this number minus that number, and this is this, and this entry is copied here. And then doing the calculation with these numbers, that's not so much fun, but you can also do that calculation. So what is that? That is minus 3.02 2.6667 times that vector again, and then this one squared plus this one squared, that's some number. And then let's do this calculation also. Please do that also with some electronic help, and then in the end you will get that matrix. I want to skip that calculation because it's not so much fun due to these numbers. Okay, then let's pack this matrix here in that block and fill 0, 0, 0, 0 and a 1 here, and then use that Q2. This is our result we had before. This matrix is that. Okay, take that matrix down to here, and then multiply with that matrix. It's also not so much fun doing it without electronic help, but then you will get that. And here we have the desired 0. And then the job is done. This matrix is upper triangular. And in total, we get Q1 times A, and then multiply with Q2 is an upper triangular matrix. We can bring that matrix to that side by multiplying the equation with Q1. And then you get Q1 times A is Q2 times R, and then multiply the equation with Q1 from the left, and you get A Q1 times Q2 times R. Okay, and then we have this Q1 times Q2, and because Q1 and Q2 were orthogonal, the product is also orthogonal. When we talked about matrices, then we learned the product of two orthogonal matrices is orthogonal. But what confused me when I was a student, or even when I was a professor, Q1 and Q2, there are a lot more properties than only being orthogonal. Q1 and Q2 were symmetric. But if you multiply two matrices which are symmetric, the product is not symmetric. Also, Q1 transposed is the same as Q1 inverse due to being symmetric, so that means Q1 is Q1 inverse, and that's called self-inverse. Multiply a matrix with himself and you get identity matrix. If that's true, then you call the matrix self-inverse. So Q1 and Q2 were self-inverse matrices, but multiplying two matrices which are self-inverse, the product is no more self-inverse. Symmetric times symmetric is not symmetric, self-inverse times self-inverse is not self-inverse, but orthogonal times orthogonal is orthogonal. Okay, so we have the following. Having a system here, A times X is B, we can reformulate So A is that product, so multiply by Q, and you get Q transpose times right hand side, and then on the left you have upper triangular times unknown x, and then you can solve the system very easily by back substitution. Okay, that was a long journey, and now we can code. I did that job for you. And what do we code? First, let's give us the QR decomposition and then apply it. And so in total, we have a coefficient matrix A and a right hand side B, and then X is the solution of the system of linear equations. And all what we have to do is use the Q we got here, multiply the right hand side by Q transposed, and then back substitution. R is upper triangular, and so this job is not very hard. This code implements the householder transformation. First, find out what's the size of the matrix, then start with identity matrix, then what's our omega, start with the first column. First we copy our matrix A and name it R, and then let's start with the first column of R. So let's start with the first column of A, and then if the first element omega 1 is positive, then use positive sign. Sign 1 means sign positive, and otherwise use sign negative. And then add to the first coordinate and sign plus or minus, and then the square root of omega transposed times omega. That's this one here. Okay. So then let's stick together our matrix. In the second step we have 1 and this block, and this is what's that good for. Start with identity matrix and then update a sub block, in our case this block here, and that's what we do here. And how do we update? By the H system identity matrix minus 2 divided by omega transpose times omega times omega times omega transposed. That's what we have here. Then collect the Q's. If we have Q1, Q2, Q3, we collect them here in the matrix Q, and then update our R matrix. In the end it's upper triangular, we named it R. Okay, I hope that does not confuse you. And then after running the loop for 3 by 3 matrix, you have to do the householder transformation 2 times, so 1 less than 3, and then in the end the job will be done. Okay, that was a really long journey, and understanding every detail, I think it's fun. Having not yet understood, then it's maybe not so much fun, but please work hard so that at least you are able to do the calculation for some given matrix. Okay, that was our first video about householder transformation.